Hi, so in this video, we're working in chapter 4, section 2, the second video, so we're wrapping it up here. In the last video, we were working on the experiment rolling 2 dice. It was a red and a black, okay? So we're still working with that experiment here, and I'm going to look at how to sort of, we're going to use ways of listing outcomes, a couple of different ways. One of them will be a Venn diagram. One will be like an ordered linear list. So we want to consider on this side of the board 2 events. The sum is 4 and the sum is 7. So we can take a minute and go back in the notes and just look at the structure of those 2 events. Okay, so I'm going to share my screen and come on up here, look at the events 4 and 7. Okay, so the events is 4 is going to be that little snaky thing that came around like that. And then the other event is 7, and it's going to be the long or snaky thing. Okay, so I'm going to go back to the whiteboard and work through these problems. We'll go back, actually, we're at the end of the notes for this section, but we will back up and cover a couple more things after we play through all of this. Okay, so the sum is 4, and we found that the way that the sum could be 4, we just kind of was looking at it, is if there's a 1 and a 3, a 2 and a 2, or a 3 and a 1. And I'm just going to list the outcomes here. And we're going to similarly list the way that we can get a 7 if we roll 2 dice. So that would be a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. So 1, 2, 3, 4, 5, 6. That's what I remember from last time. I want you to look at the way that, at all of the outcomes in event A and all of the outcomes in event B. And notice that they have no outcomes. They have no outcomes in common. So if I were going to draw this on a graph, and I'm just introducing the Venn diagrams here, we'll go back and look in the notes a little bit about them as well. But because they have nothing in common, I'm going to draw them as two separate circles on my graph. And I'm going to go and put in here the outcomes. Maybe should have made this a little bigger. We'll see how I do. Oops, looks like I left out a 4 and a 3 here. Oh, nothing says they have to be real circles. Okay. So notice that there's nothing in common, and that's how I can get away with this, with having the circles be separated. And so just remembering from last video, the probability of an A was the number of ways you can get. Probability of event A is the number of ways you can get event A, which was 3, divided by 36. The probability of event B, there are 6 ways, so 6 out of 36. Okay, let's go over and look at the set of events on the right-hand side of the board here. We're looking at the 2 events, a 4 and a double, so take a moment to go back into the notes again to look at the 4 and the double. Okay, so the 4 was this same guy over here squiggling along, but the double crosses this way. And notice that they both contain the 2 and the 2. All right, so I'm just gonna go ahead and move back to the whiteboard with that little bit of comment and reference. Okay, so let's fill out this table and then also the square. So this is going to be the Venn diagram. I'll make him a little bigger because the other guy's kind of squashed. All right, so the ways we can get a 4 and the ways we can get a double, there's one that has to be included in both of them. It's the 2 and the 2. So then other ways for the event A, 1 and a 3 and a 3 and a 1. So this is event A. And then event B, we'll draw it here. And I'm going to list all the other ways to get a double in this other lobe. 1 and a 1, a 3 and a 3. Okay. So here are our pictures. I'm going to list them on our table. You can fill this in on your notes if you like. Okay. All right, so I want to start thinking about now operations on events. What do I mean by operations? Well, if we go back to sort of just regular numbers, operations on numbers are things like addition, subtraction, multiplication, division. What we want to work with events is the event of the and, A and B, and A or B. So those two are operations. So the and event is all outcomes in A that are also in B. So the event A and B over here on the right-hand side is actually, we have something because they overlap and it's 2, 2, okay? And the probability of 2, 2, the probability of A and B is the number of outcomes in A and B, and in this case, it's just 1. So the probability of A and B is 1 over 36. Okay, the OR event, event A or event B, I'm going to take a little diversion here. So there are different ways that we use the word or, right? So when you go to get a cup of coffee, you might take cream or sugar, but I take both. All right, kind of like ice cream. All right. But when I ask you if you'd like cream or sugar, you understand that you can tell me you want cream, you want sugar, or you want both. And that way of using or where it includes the both is called an inclusive or. And that's the or that we're going to use in probability in this course, in this century, and most of last century. But in the beginning of the 1900s, the mathematics books were written with a different definition of or. Okay, so in that, the other way that we use or in English and the previous and the early way of using or in probability is that you can have, like if I ask my husband, do you want like pizza or chicken for dinner? He knows that in that case, the or means you can either choose the pizza or you can choose the chicken, but yeah, not both, okay? So sometimes we use the exclusive or, where you can have either the pizza or the chicken, but not both. All right, and so just kind of wanted to go over that because in probability theory, we will always be using the cream and sugar or. We want A or B or both. So over here, I want to list out everything that's in A or B or both, and I'm going to put that in this box here. So it's 1, 3. It's everything that's in A. 1, 3, 2, 2, 3, 1. And then everything that's in B, but I don't want to list the 2, 2 a second time. So 1, 1, 3, 3, 4, 4, 5, 5, and 6, 6. All together, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ways, 8 outcomes in the event A or B. So the probability is 8 over 36. Okay, so a little bit of that. Let's go over to this other, the other side of the board, where notice that these 2 events had nothing in common. All right, and when there are 2 events that have nothing in common, we call that mutually exclusive or disjoint. So those 2 words mean the same thing. 2 terms mean the same thing. Okay, so what events are in A and in B? Are there any outcomes in our sample space of size 36 where the sum is equal to 4 and the sum is equal to 7? No. So there are none here. I can't list any. And the probability of A and B is none. I'm sorry, A and B includes no outcomes, and so it's 0 over 36. Probability of A and B is 0. And now what I want to do also is I want to think about the OR event. So the OR event is everything that's in A. So the 3 that are in A, and then everything that's in B. Okay, and all together now we have 3, 4, 5, 6, 7, 8, 9. The probability of the event, the sum is 4 or the sum is 7, is 9 over 36. All right, I'm just going to move back over to the notes and, all right, just one more comment. Let's label this as mutually exclusive. These 2 events are mutually exclusive or disjoint, and over here, they are not mutually exclusive. I'm going to keep the board where it is. We're going to use it again in a little bit. So let's come over to the notes and just go through a few things in the notes. Okay, so more basic properties of probability. So if I were to give you probability, a probability structure that didn't follow these basic properties, you probably wouldn't be all that interested in my probability structure. So in particular, property 1 is that probabilities are between 0 and 1, including an event can have a probability of 0 and it can have a probability of 1. So you have these equal to's as well. If you asked me what the probability of an event was, and I told you that it was 1.4, then you would say, I don't want to talk to you about probabilities. So I won't do that. So we have to keep our structures of probabilities between the 0 and the 1. So property 2 is that if an event cannot occur, then its probability is 0. E is called the impossible event. An example of an impossible event is that if I roll 2 dice and I get the sum is 20, then that would be 0. Another event that would be also impossible back on the whiteboard was that if the probability of rolling 2 die and getting a sum that is both equal to 4 and equal to 7. and that can't occur. Okay. And then the last property I want to talk about for a moment is this property 3, that an event that must occur has probability 1. It's called the certain event. So an example of a certain event is to roll the die and get a sum. That's between 2 and 12. That was a certain event. We saw the probability of that occurring was 1. I just want to go through a little example of how to use data from an experiment together with probability, okay? And this is kind of where our statistics that we were looking at earlier in the course with random sampling and all kind of come to that boundary between statistics and probability. So a resident is chosen at random from a dorm, and we have the sample space of the dorm laid out here. So we have this table, it's really a frequency table, but it explains the that we have 128 freshmen, 112 sophomores, 96 juniors, and 48 seniors. Okay, and that's in a dorm. And the experiment is that we're going to randomly choose a dorm resident, and that the sample space is the set of all dorm residents. And the event that we want to calculate or consider is what's the probability of getting a sophomore. So the event is then all sophomores who reside in the dorm. So what is the probability of getting a sophomore? It's the probability of choosing, it's equal to the number of sophomores, 112, divided by 384. So it would be good here to calculate that probability and round it to 2 decimal places, because it's not cards or dice. So we want to express it usually in 2 decimal places. So that would be 112 divided by 384, rounded to 2 decimal places, 112 divided by 384. So I'm getting 0.29 or 29% for the probability of randomly choosing a sophomore. Check it one more time. %, yes. Okay. And so the other standard experiment we all have to be comfortable with is the idea of cards. Now, I know that you guys had a lot more games to play than I did, so maybe not everybody played with cards when they were had more play time. But if you haven't played with cards, I have illustrated here a deck of cards. There are 4 suits: clubs, hearts, spades, and diamonds. And each suit has an ace, and then 2 through 10, jack, king, and queen. Okay. And so what we want to do is think of if we had a set of cards and shuffled the cards, then we could randomly choose a card, and we would like to determine what's the probability of certain events. Okay. So there are 52 or 13, there's 13 cards in each suit, and there are 4 suits. So 13 times 4 is 52. So capital N is 52. And the probability that the card selected is the ace of hearts is going to be the number of ways you can choose the ace of hearts, which is 1, and divided by the size of the sample space, which is 52. Okay, and we can leave it in that form because it's cards. The probability of getting a king, how many kings are there in the deck? There are 4 kings, so 4 over 52. And the probability of getting a heart, let's grab a little bit of space here. So the probability of getting a heart is going to be the total number of hearts in the deck. So there are 13 ways to get a heart, and a total of 52 in the deck. And finally, the probability of getting the face card. So we have to just kind of define what a face card is. And a face card are these cards here that have actual faces on them. So how many are there? 1, 2, 3 times 4. There are 12 face cards. And the probability of getting a face card is going to be 12 over the size of the sample space, which is 52. Okay. A little bit more just on the Venn diagrams. We had opened it up with the simple problems on the whiteboard, but a couple more things to clean up here. We talked about A and B. If there's an overlap, then this the overlap is the AND event, and A or B is everything that's in A, everything that's in B, including the stuff that's in both. All right, this event here, the green on the outside, is the event not E. So if we have an event E, everything, this is called a complement event. The complement of E is not E, and it's the list of all of the outcomes in the sample space other than the outcomes that are in the set E. Okay, a little bit about mutually exclusive. These are a picture of mutually exclusive events where the circles don't overlap. And here is an event. Here's a picture of not mutually exclusive, non-mutually exclusive, or not disjoint, and they have some overlap piece. The little overlap piece is the AND event. If you have 3 sets or more, we would consider the first picture here mutually exclusive. And both of the pictures over here are not mutually exclusive, right? So if events are mutually exclusive, then it must be that if I know one occurred, I know for sure that the other 2 did not occur. And that is only true in this picture here on the left and not on the 2 pictures on the right. So, okay, I think that's where we want to stop for section 4.2, and I'll see you in the video on section 4.3.